So thank you again for the introduction. So you've got all of that information, and I'm talking today to give an update on genome editing therapies for transfusion-dependent thalassemia. And I think the first thing to say is there probably will be more questions than answers in this talk because there are a lot of unknowns as yet, but I'll give you the information that we have so far. So the background to this, you know all of this, there are significant unmet needs for individuals living with transfusion-dependent thalassemia. The only curative option currently is a donor bone marrow stem cell transplant, and at the moment that's only open to children. In the UK, it's dependent on having a well-matched donor, and there are some quite specific risks that come with having someone else's donor stem cells, including graft rejection and graft versus host disease. So that's not an ideal treatment by any means, even for those for whom it is an option. And for everyone else, lifelong transfusion and iron chelation are unavoidable, with all of the potential complications, side effects, and burdens of treatment that they bring. And we do know that quality of life is significantly affected by those requirements. For example, many people live with daily pain, and I think a lot of these complications are under-recognised and under-reported. And sadly, there is still a limitation to life expectancy. So all of that is to say, we need better treatment. The background and the reason that we can use a patient's own stem cells to help cure thalassemia, this graph just shows that all of our mature blood cells, including the red blood cells, white blood cells, platelets, they all come from this really early pluripotent stem cell, and they're housed in the bone marrow. So those cells repopulate all of our more mature cells. So if we can get at that stem cell, and if we can, in one way or another, correct the genetic problem causing thalassemia, then we anticipate that all of the cells that come from that really early stem cell, or all of its descendants, will be corrected. So that's the rationale for correcting stem cells to treat thalassemia. And the first way of doing this, you probably heard about gene therapy, lentiviral gene therapy, and Bluebird were the company primarily leading on this. This is going back just a few years now. So that's one way of doing it that we're not focusing on today, but for completion, the way that works is, and pardon the cartoons, I drew these myself, and art is not a strong point. But this is a little virus, a viral vector, the green spiky thing, and it's carrying a copy of a corrected or modified beta globin gene, and it's added to the stem cells, and this is the stem cell here with its nucleus and its DNA, and the viral vector delivers that new or corrected gene copy to the cell, and that's integrated in that cell's DNA. So that's the first way of doing it. Now, Bluebird have pulled out of the European market. This is not an option for UK patients, and isn't going to be in the near future, but I actually think that genome editing is a better option, and the reason for that is that with lentiviral gene therapies, this DNA integration is always going to be at least semi-random. So we can't target, we can't decide exactly where in the genome that's integrated. And the problem with that is that usually it's in an area that isn't particularly vital, and that's fine, and it's not the end of the world. But there's at least a theoretical risk that that could interfere with a really vital area of the genome, that could potentially predispose someone to future cancer. And for those reasons, I think genome editing is a much better way of doing this because it's much more targeted. And my research was in genome editing, so I confess to possibly being slightly biased, but I think this is a safer therapy. So genome editing works by really targeting the DNA. We think of it as molecular scissors because it causes a double-stranded DNA break in a very specific area of the genome, and it can be much more specific than the other type of gene therapy. And there are various ways that genome editing can be delivered. These are some of the older ways. The leading way now is CRISPR-Cas9, which you may well have heard of, and it's CRISPR-Cas9 genome editing that Vertex, the company investigating this in the UK, is using. So it involves having a very well-matched section of genetic material that will guide the nuclease or the molecular scissors to the patient's DNA and snipping it in exactly the right place. Just for interest, this is the timeline of genome editing technology, and you can see it's really come on in leaps and bounds within a few decades, really. So this is a natural system that's already present in bacteria, and so it's harnessing the power of that natural system, and that was recognised back in the 1980s. And then by about 10 years ago, we're seeing application of CRISPR-Cas9 to human cells. So that's really very quick development in medical history, really. And there are a few ways that CRISPR-Cas9 can be used to treat transfusion-dependent thalassemia. The first one, and the one that's come the furthest and the way of talking about today, is used to disrupt genes which control that natural switch from fetal hemoglobin, which we rely on before birth, to adult hemoglobin. And that switch happens during the first few months of life, but for people with transfusion-dependent thalassemia, that can't happen successfully because there's not the ability to make that healthy adult hemoglobin. So if we can just reverse that switch, and if we can switch back on the production of fetal baby hemoglobin, then the lack of adult hemoglobin is going to be much less problematic. So that's the most successful way of doing this to date. There are a couple of other ways that genome editing can be used to treat thalassemia, and these are just mentioned because other companies, other researchers are looking into these other ways of doing it. So I think you'll hear about various other strategies in the future, but let's focus on this initial way, which is disrupting the gene and reversing that switch to switch back on fetal hemoglobin production. Now, the next few slides are from Vertex, so I should credit them with the information. That's the company that's led on the CLIMB thalassemia trial of genome editing. I've made some modifications for clarity, and I have no vested interest in the company, I should say. So this slide shows the exact area of the genome that's being targeted, and it's part of this gene called BCL11A. And if we knock out just the right area of that gene using CRISPR-Cas9 genome editing, then those cells don't produce this protein called BCL11A. And if that protein isn't produced, then the fetal hemoglobin production switches back on. So that's how this works. And here are the practicalities of having treatment with this particular genome editing therapy. And this is from the trial. So the screening would still take place because even if this is approved, there will inevitably be eligibility criteria. So the first step would be to make sure that this was the right treatment and someone was eligible for it. They would then have medications to make the stem cells, which live in the bone marrow, start circulating in the peripheral blood, and that's so that they can be taken out of a peripheral vein. So the blood would come out of a cannula, it would go into a machine which spins it down and extracts the stem cells. That's what's happening here in stage 2. And then the rest of the blood goes back into the patient through another cannula. And those stem cells are then taken off to the lab where they have this CRISPR-Cas9 editing treatment. And after testing to make sure that that's been successful and the cells are good quality, they would then be returned to the patient. Prior to that, though, this individual would have some really strong chemotherapy called busulfan to essentially clear out the bone marrow and make space for those modified stem cells to be returned. And a stem cell infusion looks a bit like a blood transfusion. Just it hangs up and infuses through into the peripheral blood, and those stem cells find their way to the bone marrow, set up home, and then start making all of the mature blood cells. The trial, which we're going to talk about, looked primarily at how many people were transfusion independent after treatment. That was their primary endpoint. And they had a few others, including, very importantly, safety endpoints as well. And we'll have a look at that data here. So these are the people who were included in the CLIMB study. So you can see there were 48 individuals with transfusion-dependent thalassemia treated with this genome editing therapy. Various genotypes included, so it wasn't restrictive in who was included. And you can see that 16 children and 32 younger adults were included, and they did have an age range of just 12 to 35 for treatment in this trial. Patients had to be transfusion dependent, but they just defined that by, for the adults, needing at least 10 years a year. So again, not particularly heavy transfusion requirements. And I think the really key outcome here is that of the 27 patients who were treated long enough for full assessment, 24 were transfusion free for at least 12 months after treatment. So very, very promising results here. And this gives a little bit more detail about each of those individual patients. So, sorry, it's a really busy slide, but each of these bars represents one patient. You can see their participant numbers down the side. And here you've got the amount of time since they had this treatment, which is called exa-cel treatment. The red bars at the beginning show the time that patients needed regular transfusions around the time of that treatment. And then the grey bit of the bar is the time it took for those donor red cells to be out of the system. And then the green bars represent the length of time that these individuals have been free of transfusion. So you can see that for the majority of patients treated, other than the 3 that we've mentioned, they've had really good times of being transfusion independent since treatment. And even those 3 patients who haven't met that primary endpoint, we've got some more information about them here. 1 has managed subsequently to stop transfusions 14.5 months after treatment, so that was maybe just a delayed effect. And 2, while still requiring some transfusion, have had significant reduction in their red cell requirements, so 80% and 96% reduction in transfusion requirements. So even that is a huge, hugely clinically significant and is going to improve quality of life. So I think these data are looking really, really good. And you can see that we're not just talking about people sort of scraping by with a really low hemoglobin that they can just about manage. People have got really good, healthy hemoglobin levels. Average was over 12 or 120 grams per litre in new money 6 months after treatment. And most of that hemoglobin is the fetal hemoglobin that's been switched on, as we'd expect. So this treatment's working really well. And this is looking at the genetic editing. So they've looked in peripheral blood to see how many of the cells had that change that they wanted to make. And I think most importantly, when they've looked in the bone marrow, they've seen, well, firstly, good levels of cells with that genetic change. But really key here is the fact that the level of the cells with the change is very nice and stable over time. And that tells us that this isn't something that's going to work for a short period of time and then probably wear off. This looks like they've edited those really early stem cells, which live for in the long term in the bone marrow. And so, although the longest treated patients is about 3.5 years after treatment, I anticipate, based on this data, that this is a permanent cure for the patients who've responded. They've looked at various patient reported outcomes, the quality of life measures. And again, these are looking really good, particularly by the time that people get to 2 years after treatment, probably when they're over the transplant procedure itself and the side effects of any chemotherapy have worn off, and really starting to live without transfusions, and that's become a reality for them. Safety data, really, really important. So it's looking effective, but is it safe? Well, the complications that people are having are generally in keeping with the strong chemotherapy that they have to be given for that modified stem cell transplant. AE means adverse events, so that's any sort of complication or side effect. SAE are the serious complications or side effects, the sort of thing that would have to bring someone to hospital or keep them in hospital. And there are a number reported, but that's what we would expect when someone's been given this really strong chemotherapy and the bone marrow has been wiped out for a period of time. There were no deaths in this study, and that's really key. So everyone came through that and came out the other end. There is a similar trial in sickle cell disease, and there was 1 death in that trial, and that was related to COVID-19. So it's worth bearing in mind. This is a big undertaking. It is a significant process for someone to go through, but the outcomes are looking good here. So I think the benefits are really clear, and that this is the possibility of a cure for the majority, or a very significantly reduced transfusion requirement for those who don't quite get to the point of being transfusion independent, and it's a one-off treatment with long-term effects. We can see that people have a better quality of life after they're treated. And by using someone's own stem cells, not relying on a donor for a stem cell transplant, firstly, you avoid the need to find that donor, which can be really difficult. And And secondly, you avoid other risks such as graft versus host disease, which is a really quite significant complication if that occurs post-transplant. It's a very targeted therapy. That's why I think it's better than the lentiviral gene therapy. I think we have to acknowledge the limitations, though. It is an intensive process to go through. So it's a bit like having a bone marrow transplant, but just using someone's own stem cells. And that does carry certain complications and risks. And so this is probably not suitable for people who have significant organ impairment or who aren't particularly fit going into that procedure. We have to anticipate an impact on fertility in the same way as a donor stem cell transplant would be expected to reduce fertility. And so I think for younger patients who haven't yet completed a family, fertility preservation will be appropriate. So for adults who've been through puberty, that's sperm storage or egg cryopreservation, or possibly embryo freezing if that person has a partner. But for children who've not yet been through puberty, it's more difficult. They can take an ovary from a prepubescent girl and freeze it and use that tissue to help her regain fertility at a later date. For boys, they can do a similar thing with testicular tissue, but there haven't yet been any successful pregnancies using stored testicular tissue, so we can't guarantee that would be successful. Really important to point out that even if someone's cured of thalassemia, that doesn't alter the genes that they would pass on to the next generation. So the inheritance risks are still there. And this is only for people with beta thalassemia. Now we know that most people who are transfusion dependent have beta thalassemia, but a minority will have alpha thalassemia, and unfortunately this would not be a helpful treatment for them. And then of course we don't have decades of data yet because this is a relatively new treatment, but that will come with time. So I feel very strongly that this is an option that should be available to patients where it's the right thing for them, where it's an appropriate treatment, and where they would wish to undergo this, albeit it's not going to be the option for everyone. And I think there's still a way to go. Even if this is approved and available, this isn't the end of the journey towards best thalassemia treatment. It's just one really big step towards it. I think in the future, we know that research teams are already working towards delivering a treatment like this without the intensive chemotherapy, and that's going to take away quite a lot of the side effects and risks, for example. So this is a hugely positive step, and I'm very keen that it is made available to patients, but it doesn't mean that we have stopped working towards something even better. So I did mention there were a lot of unanswered questions. We just don't know yet whether this is going to be available in the UK. NICE are currently assessing the evidence, and Vertex have made submissions to them, and I'd anticipate a decision next year, hopefully early in 2024. We have to acknowledge that cost is going to be a major consideration that NICE will take into account. So to some extent, this is a political decision, so really our Member of Parliament here. If it is approved, we still don't know who would be who would be eligible for treatment. So will the approvals follow the clinical trials with that age range, 12 to 35? Will it be more lenient, more a matter of clinical judgment? I'm sure that there will be something regarding iron control, because it would be less safe to go through this type of process and this treatment without well-controlled iron. But again, we just don't have that information as yet. So in the meantime, despite all those uncertainties, what can you do? Well, firstly, please do think about contacting your MP if he's not in the room, to ask them to support this treatment being available for individuals with thalassemia. And secondly, look after your health. Stay as well as you can, maintain good iron control, so that if hopefully this treatment is approved, then you'll be in the best position to receive it. Okay, well, thank you very much.
And so I applied to the NIHR HIC to say, can we have one on transfusion-dependent anemias? And again, here's a QR code if you're interested. And what this will do with my diagram that took me forever, we'll bring together transfusion data. It's all anonymized and it's all done, we've got ethical agreement, to a trusted research environment. to understand what blood people are getting, what their blood groups are, how often they're being transfused, whether they're having reactions, what their underlying problems are, and then some sort of demographics, how old they are, whether male or female, to really understand what the risks are to patients and how we can best prioritise matching. I mean, this is dull but essential. So we know that for, I mean, I've talked about it at the beginning, our systems are not joined up. And if we want to do a really beautiful system of, you know, linking patients to donors and donors to patients and understanding whatever the whole history of someone's transfusion history, wherever they might be in the country, we need better IT. I don't think we'll sort that initially. I think once we can show the other things are working, that's because this is proper money. So this is the fun bit, and this is a bit a lot of people get excited at when we do our talks. We've applied for funding from the NIHR for an artificial intelligence grant, and to see if we could apply AI to blood matching. So the concept is that if you're a patient, you get your blood group genotyped. We know we can do that. There's a thing there called blood type, and just to say that the reason you have that there is the platform that I've been talking about by the Blood Transfusion Genomics Consortium produces a bunch of DNA code. Now, I don't understand any of that. Someone needs to make that into a blood group that I can recognise, and that's what this bit of IT, some very clever people have designed to convert the DNA code into a blood group, and it sits in a database. And we've already got everyone's blood group in the database in the blood service anyhow, so that's not conceptually that different, except we're doing it to a lot more people. And then we do the same to the donors. And then what happens is, in this system, is the patient comes in for a transfusion, and we put the request in, and the algorithm searches for the best match units for that patient and allocates them. Later down the line, what we want to design is blood stocker, which would make sure that that people are pulled for blood donation on the basis of their blood group, so that we have the best donors for our patients. And actually, for some donors, they might not need to donate at all, and some donors we really need to look after. We do that a bit at the moment, but it's very manual. You know, we phone up special people who've got really weird blood groups, but we want to do it in an automated fashion. So other work that we're doing is to make sure that we've got really good public involvement and engagement in our studies, because it's for the public, it's not for us. And so we've got some really fantastic people, thalassemia and sickle, on that group, who really put us through our paces, but provide some real insight as well. I also want to, when we get closer to delivery, start talking about laboratory stuff, because it's going to have a big impact on how they deliver their care. So at some point, and we're designing this now, we need a feasibility study. A feasibility study is when you take a small group and you see if conceptually your idea can work at all before you go out to a big clinical study which shows that it improves patient care. So we want to show initially that our algorithm can allocate blood. It would be completely controlled by humans at that stage as well. And these would be people who'd consented to be part of a feasibility study. This won't just randomly happen to you. You'd be well aware and fully consented. If we got that far and we showed that our algorithm that we've designed can do that and can do it better. At the moment, it's showing that it does it better than the people. We need to show that in a sort of study environment rather than just not a fake environment, but we're not actually allocating, we're telling our machine to allocate and seeing what it comes up with. Then we would again have to make sure that it reached the appropriate standards to be signed off as appropriate for clinical care. And that would involve a much bigger study. So we've got a really big study group. That's actually not the slightly old set of pictures, but there's lots of us doing lots of really good work. And it's quite a mixed, eclectic group. So prior to getting involved in this kind of work, I was very much involved with just sort of doctors and lab people. But now, of course, I need software engineers, bioinformaticians, geneticists. So it's quite a broad set of people, and it's been Really exciting, actually. I've learned a lot. So how could we get red cell genotyping? How can we get this new big machine that we've got that can do all these fancy testing and that the NHS is paying for you guys to have it free? How can we make it mean something meaningful for patients to change their and improve their outcomes? So the only way to really do it is to have the cost-effective, cheap donor genotyping, and that's something we're doing. We do need to change the way we procure, allocate, and distribute blood. And we've talked a little bit about what that might mean for blood donation and connectivity. We need to evidence-base our system. There's a lot of guidelines out there that say just do more. And actually doing more without it being helpful is just a waste of everyone's time and of scarce resources, and sometimes can lead to delay. And delay can be really bad for patients. We need it subject to public and patient engagement group activity scrutiny. So we want people in our group, our patients, to say, actually, no, I don't want it done like this. What about X? What about Y? So we want to do that. And I mean, I heard you all talking about gene therapy, and there were lots of very coherent arguments about why patients deserve it. But all NICE care about is health economic advantage. They care about the bottom line, the financial bottom line. It's not that they're mean people who don't care about people suffering. Their sign-off is about quality adjusted life years. And unless you meet that, you're not going to get them to pay for anything. And so I think we need to be quite dispassionate about how we do this. And I've got one theme of this is health economics. We're working with a bunch of health economists at UCL to look at the current cost of blood provision and what it looks like if we automate some of it. So what can patients do to sort of support this process? So firstly, I'm slightly anxious that as soon as this test is available, no hospital's going to be ready to order it. So please check in with your clinical team. They all received a letter last week from the NHS saying, get your systems ready. So please help them focus and get the systems ready so they can send off the test. And then when you come for blood testing, come October, when it's rolled out, there'll be some song and dance NHSE will want to do, and not song and dance, some marketing and comms. So you'll hear about it. Then you need to be asking people, reminding them to do this test for you. If you're interested in doing PPI work, then please do get involved. The patient voice is really, really important when it comes to research. And then just a little thing here is that when I talked about our database, we can't include anyone who's opted out of the NHS data agreement. So if you opt out, then your data isn't included. And in my hospital, that's a third of thalassemia patients. So we're losing a lot of data to support our patient cohorts. We are allowed to write to our patients and say, would you like to opt in just for this study? But that's really cumbersome to do. And you know, a lot of places we won't have the bandwidth to do that. And the less patients are represented in their disease group, the less accurate and helpful their data will be. So just understanding what that means. I understand why people do opt out of the NHS for data, but it does have a direct impact on what we can do for small patient groups. If you're boring and, you know, the same as everyone else, then it probably doesn't matter. You're one of a million, but you guys are one of 800. So opting out is a massive impact on what we can learn. These are some of the people across both England and different national blood services in the States and Holland and South Africa, Switzerland and beyond, who've been absolutely key in developing some of this work. So basically, I want to say a big thank you. And there's some websites to learn a bit more, and I will stop sharing.
Thank you, Sarah. This is thank you. Thank you very much for the work done. This is a game changer, so really appreciate it. Hopefully, we can get more people opting in to the research. Can you hear it? Okay, anyway, thank you, Sarah.
I heard a really nice thank you, Gabriel.
just to say thanks to Claire, who was answering the question, Sarah, during your presentation, to the ones asking it online. So I think people asked about blood. What I was trying to spy on it, but it was about blood volumes. I think one question.
Can I just answer the question about blood volumes, because that's just to be clear. Your circulating volume is 70 mils per kilo. So if you're, say, 50 kilos, you've got 3.5 litres of blood in you. The average volume, the mean of most units are 260 mils. That's the average. And some will be more and some will be less. Very few will be a lot less and very few will be a lot more. But in reality, if you're an adult and you're getting 3 units and one of them is 40 mils difference with your, 3.5 litres of blood around you, that is not going to make a big difference. It just isn't. And what happens is that if you start fiddling around with the blood units that are in the fridge, you run the risk of, start having units out of the fridge for too long, which is really bad for the how well the blood lasts. There's really strict rules about how long blood can be kept out of fridge. And if you keep pulling out of units out of fridge to check volumes, that's a bad idea. And also, it's just not something within the breadth of the ability of the blood service and most blood centres to be sort of filtering through hundreds and hundreds of units to get you the slightly bigger unit. The only time it is possibly a bit more important is around small children who, when you're calculating their blood volume that they need, you do it in mils per kilo, and say that it's 320 and you've got a 280 unit, you've almost hit it. But if you've got a 230, that's percentage wise quite different, and they've got a much smaller circulating volume. So I wouldn't focus too much on blood volume of units. There's many other things. I mean, part of the things in the past that was very concerning about blood volumes was that if you've got bigger units, you'd get less units overall in a year. Now, and the issue with that was issues of transfusion transmitted infection, which is obviously less of an issue nowadays, and chelation. And obviously iron loading now is entirely related, not to how much blood you're getting necessarily, but how well you take your chelation, if it's been given at the right dose and taken at the right dose. So I would not focus on, it's just not within the capacity of the blood service to be pulling out units, because it's a normal distribution. So most people are around 260, give or take. There are very few very big units.
How about the quality of the blood? How old should it be?
How old should it be?
I mean, what's the oldest unit we can have? Is it up to 10 days or?
No, so blood service. So we are according to, I wrote round to all the different blood service and said, do you have issues, rules around age of blood for your patients? And the answer was no. So we're the only country that really sticks to this, and it's not well evidence-based. It was relevant very much in the past. Now, remember, the blood service doesn't issue blood to a hospital that is more than 2 weeks old anyway. So the blood is not being issued to your hospital that's older than 2 weeks. If it's older than 2 weeks, it's been sitting in your hospital. So, which is not great stock management. Sometimes that will happen a little bit, but overall it shouldn't really happen. The issue of age of blood, if I'll just finish and then ask your question, the issue about age of blood was very much to do in the past with when we had different reagents, less quality control around cold chain, around the processing pathways. We used to have plasma with blood, we used to have white cells with blood. The product now, it looks very, very different and is much more precise and cleaner and better looked after than what you would have had, a lot of you, earlier on in your life. It's a very different product in many different ways. It's a much higher quality product. We looked very much at the peak and trough hemoglobins in people in a big cohort of patients from UCH and Whittington, and there was no difference. The age of blood didn't vary that much, but there was no difference in the next hemoglobin, in the change in hemoglobin you had pre-transfusion and then the next transfusion, according to the age of blood at all. So a lot of the things, this is what we're talking about, is they're historical. They had good reasons to be important back in the day when there were lots of different issues. If you if you were worried about a significant risk of a transfusion transmitted infection, you really didn't want an extra unit because that would definitely increase your risk. But things are very different now. You want the best matched unit. That's the biggest risk to our patients now, is matching. And when you start adding in other criteria, you reduce the chance of matching. And we see this a lot in sickle, which is that if you ask for a younger unit, you're much more likely to get blood that is from with blood groups that are completely alien to you and much more likely to develop an antibody. So as we understand the system better and the risk to patients better, we need to adjust how we think about what we want for our patients.
Just one more thing, about the ethnic of the blood, would that help? Would it help us? The
So
ethnic of the blood. The donor of the ethnic it's coming from the, yeah, is that it?
So I think it's really interesting. So ethnicity, there's self-declared ethnicity, which is what you feel like you are, and there's what you genetically are. What it really matters is what your blood groups are. And the biggest issue is mostly for people of African descent. So Black people have often quite a different spectrum of blood grouping than other people. And then for the rest of us, it's pretty here and, you know, it's pretty broad, but we have a lot more, we're positive for more. It's better to be positive for a blood group as a recipient, because then when you receive that blood group, it's not foreign to you. Whereas if you're Black, you're much more likely to be negative for blood groups. So it's less of an issue. Most antibody formation in people with thalassemia is historical. So it's people from a long time ago before we did better matching, often people from abroad. So that new antibodies in thalassemia is quite rare. So I don't, you know, at the moment we think about ethnicity, but what we really should think about is, I don't really care what, you know, church or mosque you go to or what the colour of your skin is. I want to know what's on your DNA for your blood group, and that's what's important for patients.
Well, I'll say that, sorry, the reason why I just mentioned that is because I know they advertise it more for sickle cell that
Yeah.
and it'd be easier for the patient. So does that work with us as well with the Australians or not?
No, because people, so when we did, if you read, it's a bit terse and dry, but we did something called the hemoglobinopathy survey. It's a published paper, and we looked at the blood groups of people with thalassemia and sickle, amongst a lot of other things actually. And the blood groups of people with thalassemia broadly reflect our donor population anyhow, which is over 97% white. So it doesn't, being Asian or Middle Eastern or Southern European or Persian doesn't seem to make it difficult to transfuse you particularly.
Okay, I think
Not that we're leaving out people with thalassemia, it's just we can usually find the blood. I'm never up till 1 a.m. like I was 2 nights last week, having chats about ferrying blood from across the country for a thalassemia patient. It's always for sickle.
Okay, so I think we do have any more questions. I say we don't have any more. I think it is Sarah and Claire, thank you very, very much. I know Gaz has said it many times, but again, it means a lot. I think we've learned a lot. What I got from Sarah's presentation is that it's life changing what's going to happen, and the fact that lots of us have reactions and problems. Yeah, and yeah, lots of us have reactions. I know I had to get HLA matched blood, and it took, I think, a year to find that blood. Because they weren't looking at that. So I think it's going to be it's life changing for us. And I think we also need to look at evolving how we think about the blood products, like Sarah said. You know, now we don't want to have to think about blood being under 5 days old to use it because it's being kept better than it was and preserved better. But it's just like how back in the day when you got whole blood, because that's what they thought was safe, and then it evolved. So it's going to continue to evolve, and we have to evolve with that. And I think this is really exciting. This is great news. I'm glad we are included in this. There's one more question.
I was just going to say, you know, when you did the question about the genotype and all the, you know, the different tests, what happens for the older patients that did have whole blood and given white cells at a younger age? Does that affect, you know, like the test that you
No, white cells only live for about 8 days. So they've been chewed up.